friends, welcome back to your favorite YouTube channel, Tomachang Tutorial. Myself Kisan Kulum, and today we are ready to go for a new topic in physics, that is thermal expansion of liquid. Okay, we have already completed about the thermal expansion of solid. Please find the link below in the description and watch that video again. Okay, now we will move on to the topic thermal expansion of liquid. Let me give example. When we heat milk, this is milk, okay, we must have noticed when we continue heating milk, the volume of the milk increases, and if you continue heating milk, the milk spills over the container, isn't it? When milk is heated, the volume of the milk expands. Before that, let me make you clear that liquid do not have its shape and size, so the superficial expansion and linear expansion of liquid is not considered. We only consider the expansion of volume, okay, because liquid do not have shape and size. Okay, now let us come to the point. When we heat milk, the milk spills from the container by increasing its volume. Means from this example we came to know, or we knew, that the volume of the liquid increases with the increase of amount of temperature, or when you heat liquid, the volume of liquid increases. Okay, this is called thermal expansion of liquid. I hope you got this. Let me give you another example. All of us have seen a clinical thermometer. This is a drawing for clinical thermometer. Clinical thermometer. This is a clinical thermometer. Though my drawing is not so good, but I'll make you understand. I'm very sure I'll make you understand this. This is a clinical thermometer, and this is made out of either glass or plastic, okay, transparent plastic. And there is a hollow space inside this clinical thermometer, okay, and inside the clinical thermometer there is a liquid metal called mercury. This is a liquid metal called mercury. Okay, when we fall sick or when we suffer from fever, doctor or nurses, what they usually do is they put this thermometer inside our mouth or under our arms, isn't it? So after some time, when we see that thermometer, the level of this mercury rises up here, suppose 40 degrees Celsius. We all know that normal human temperature is 37.5 degrees Celsius, but the level of this mercury rises to 40 degrees Celsius, means we are suffering from fever, or body temperature is higher than the normal temperature, isn't it? But my point is not that. The concept I'm trying to tell you is this liquid mercury has expanded by the heat from our body. Liquid expands on heating. Our body provided heat to this mercury inside the thermometer, so that this liquid metal expanded in volume. Got my point? Liquid on heating expands. I have already given you two examples. I hope you got my point. Every liquid, not only milk or mercury, but every liquid expands on heating. Okay, now let us move to the topic coefficient of apparent expansion for liquid. Okay, expansion of liquid. When we talk about the expansion of liquid, when we heat liquid, we cannot heat liquid alone. Liquid must be in a container, isn't it? Liquid must be in a container when we heat liquid. So when we heat liquid, suppose this is the new volume. Originally volume was still here, and now the level of the liquid has increased this much, and this is the new level. Okay, the volume of the liquid has increased. You can see in this figure the volume of the liquid has increased. But if we consider only the increased volume of the liquid, if we consider only the volume increased of the liquid only, then that type of expansion is called coefficient of coefficient of apparent expansion of liquid. This is the coefficient of apparent expansion of liquid. Apparent expansion. This is apparent expansion, okay? Not the real expansion. Why? The reason is, when you heat liquid, not only the liquid, but along with the liquid, the container in which the liquid is contained, the container also expands, isn't it? The container also expands, so we must consider the expansion of container also. So if we take into consideration the expansion of container along with the expansion of liquid, and that expansion is called the real expansion of liquid. I hope you got that. Let us move to the topic right now, apparent expansion, in which expansion of liquid only is considered, okay? Only the expansion of liquid is considered, expansion of vessel is not considered. We do not consider the expansion of vessel in this case, we consider only the expansion of liquid, okay? Let me read out the definition. Coefficient of apparent expansion for liquid. It is defined as the ratio of apparent increase in volume of the liquid to its original volume for every 1 degree rise in temperature. For every 1 degree rise in temperature, the fractional increase in volume of the liquid is called coefficient of volume expansion of liquid. Fractional increase in volume means increased volume divided by original volume. Fractional increase in volume means increased volume divided by original volume, okay? Now let me deduce the relation and make you understand there. Please take the screenshot of this definition. Okay, let the volume of certain mass of liquid be V1 at theta 1 degree Celsius and V2 at higher temperature theta 2 degrees Celsius, okay? Let us consider V1 be the volume of the liquid at temperature theta 1 degree Celsius and V2 be the volume of the liquid at higher temperature theta 2 degree Celsius. So, rise in temperature is how much? Theta 2 minus theta 1, isn't it? Let me explain. Originally, the temperature was 5 degrees Celsius. Now, the new temperature is 8 degrees Celsius. So, rise in temperature is 8 degrees Celsius minus original temperature 5 degrees Celsius, isn't it? When the temperature increases, the volume of the liquid also increases. That means V1 is lesser than V2 or V2 is greater than V1, isn't it? So, increase in volume. Suppose originally the volume was 5 liter, now the volume became 12 liter. So, the increase in volume is how much? 12 liter minus 5 liter, isn't it? That is 7 liter. We find the increase in this way. Okay, now let us begin. For theta 2 minus theta 1 degree Celsius rise in temperature. Rise in temperature is theta 2 minus theta 1. Original temperature was theta 1. Increased temperature is theta 2. So rise in temperature is theta 2 minus theta 1. Rise in temperature, apparent increase in volume of liquid equals to V2 minus V1, isn't it? Got my point? So, unitary method for 1 degree Celsius rise in temperature, apparent increase in volume of liquid equal to, in suppose 20 apples cost rupees 80, then cost of one apple will be this 80 upon 20, isn't it? So that is 4. Got my point? Similarly, for this temperature rise, this was the increase in volume. So for 1 degree rise in temperature, V2 minus V1 divided by theta 2 minus theta 1. Got a point? Just the unitary method. Therefore, fractional apparent increase in volume per degree rise in temperature. This is the definition of coefficient of thermal expansion of liquid, isn't it? Coefficient of thermal expansion of liquid. The definition of coefficient of thermal expansion of liquid. Fractional apparent increase in volume per degree rise in temperature equal to V2 minus V1. Fractional means increased volume divided by original volume. Per degree means theta 2 minus theta 1, isn't it? V2 minus V1 by V1 into theta 2 minus theta 1. Okay, this is the definition of coefficient of apparent expansion of liquid. So coefficient of apparent expansion of liquid is denoted by letter gamma A. Okay, coefficient of apparent expansion of liquid, apparent volume expansion of liquid is denoted by gamma A. This is the value of gamma A. Okay, now SI unit of coefficient of apparent expansion is unit of volume is comes in the numerator, and unit of volume is also in the denominator. So this unit and this unit gets cancelled. Only the unit of temperature remains. So SI unit is per Kelvin, and CGS unit equals to per degree Celsius. Okay, I hope you got my point. Now let us find the new volume of the liquid, that is V2. Please take the screenshot of this. I am going to erase this. New volume of the liquid V2. Okay, since gamma A equals to V2 minus V1 upon V1 theta 2 minus theta 1, isn't it? So let us cross multiply this, or gamma A into V1 theta 2 minus theta 1 equal to V2 minus V1. We cross multiplied the denominator in the left hand side. Okay, or let us bring this V1 to the left hand side. Gamma A V1 theta 2 minus theta 1 minus V1 becomes plus V1 equals to V2. I hope you got this. This is very simple calculation. Or you take this V1 and V1 common, V1 common, within the bracket remains gamma A theta 2 minus theta 1 plus V1 is out, so remains 1 equal to V2. So the new volume of the liquid V2 will be V1 into gamma A theta 2 minus theta 1 plus 1. This gamma A depends upon the nature of the liquid, and this is the rise of the temperature. Okay, V1 is the original volume. I hope you got this. Okay, now let us move to the new topic, real expansion of liquid. Okay, we have already completed apparent expansion of liquid. Now we will move on to the next topic, real expansion of liquid. We know that when liquid is heated, along with the liquid, the vessel in which the liquid is kept, the vessel also expands. So if we take only the expansion of liquid into consideration, that type of expansion is called apparent expansion of liquid. But if we correct the apparent expansion of liquid with the expansion of the volume, then that type of expansion is called real expansion of liquid. Now let us move to the topic, real expansion of liquid. Okay, coefficient of real expansion of liquid. In this type of expansion, we consider the expansion of liquid and the expansion of vapor as well. Okay, let us read the definition. It is defined as the fractional real expansion in volume of the liquid for 1 degree rise of temperature. For every degree rise, fractional increase in volume of the liquid, fractional increase in real volume of the liquid for every 1 degree rise in temperature. Fractional increase means increased volume divided by original volume. Okay, please take the screenshot of this definition. I am going to erase this and deduce the coefficient of real expansion of liquid. Let V1 be the volume of certain mass of liquid at θ1 degree Celsius and V2 be the volume at higher temperature θ2 degree Celsius. Okay, we are considering volume of the liquid V1 at temperature θ1 degree Celsius, and when the temperature increases to θ2 degree Celsius, the volume also increases to V2. Okay, so very simple, we do as before. For θ2 minus θ1 degree Celsius, rise of temperature for θ2 minus θ1 rise of temperature, real increase in volume. In this case, we consider the increase in volume of liquid and increase in volume of the vessel as well. Okay, θ2 minus θ1 degree Celsius rise of temperature, real increase in volume of liquid equal to V2 minus V1, isn't it? So unitary method now. For 1 degree rise in temperature, real increase or expansion, you can write expansion, real expansion of volume of liquid equal to V2 minus V1 upon this θ2 minus θ1 comes down, unitary method, θ2 minus θ1. So fractional increase in real, fractional real expansion of liquid. Okay, fractional real expansion of liquid per degree rise in temperature equal to, this is the definition of coefficient of real expansion of liquid, isn't it? Fractional real expansion of liquid per degree rise in temperature equal to V2 minus V1. This is the increase in volume, so divided by original volume is fractional increase, and per degree means θ2 minus θ1. Got my point? This is the definition of coefficient of real expansion of liquid. fractional real expansion of liquid per degree rise in temperature is the coefficient of real expansion of liquid, and it is denoted by gamma R. Okay, gamma R equal to this. So coefficient of real expansion of volume of liquid is denoted by gamma R equal to V2 minus V1 by V1 into theta 2 minus theta 1. Now unit, let me erase this, please take the screenshot of this. Unit of gamma R, unit remains same, unit SI unit equal to unit of volume divided by unit of volume cancels out, so unit of temperature remains, that is per Kelvin. So Celsius unit equal to per degree Celsius. I hope you got my point. Now let us find the new volume of the liquid V2. Okay, V2. Since we have gamma real equal to V2 minus V1 upon V1 theta 2 minus theta 1, isn't it? Let us cross multiply this. Gamma R into V1 theta 2 minus theta 1 equal to V2 minus V1. Now let us bring this minus V1 to the left hand side, or gamma R V1 theta 2 minus theta 1 minus V1 becomes plus V1 equal to V2. Now let us take V1 common. So gamma R into theta 2 minus theta 1 plus 1 equals to V2. So new volume of the liquid will be V1 into gamma real. Gamma real depends upon the nature of the liquid and the nature of the vessel in which the liquid is contained. Okay, and this is the rise of temperature. Now I hope you got this. Please take the screenshot. Thank you so much for watching this video. I hope you liked this video and understood the concept which I tried to teach you in this video. Stay tuned. I will upload more videos like this, and please don't forget to subscribe and click on the bell icon to get notifications for more video uploads. Thank you.